Good afternoon, this is Schweitzer. We're going to run a little video here on what's called Lechat's principle. This is a pretty straightforward idea. If you're struggling with it and getting problems wrong, you should come talk to me and usually get this thing straightened out pretty easily. Sometimes the hardest part about this is just spelling Lechat's principle. Sometimes I just refer to it as Lechat. Okay, what is it? It's basically a non-math version of this. Right? It's a non-math version of Q versus K. So what it basically says is that if you, let's say, sometimes I'll make a human example of this, where if a person, let's say, is standing up and you knock them over, okay, they will take a moment and then rewrite themselves. So if you are at equilibrium, okay, and a stress is applied. Now, by stress means that is applied, okay, then the reaction is knocked out. So we're saying you're at equilibrium, which means your Q equals your K value, your equilibrium. A stress is applied, so now your Q does not equal K value. Then your reaction will shift. Okay. So on this little table here, we're actually going to product. You're at Q versus K. You're here. Okay. A stress is applied that shoves you either here or shoves you here. And then you will shift, meaning you will go this way or you go this way to get back to K. And you'll shift to return to K. So a couple things here. First of all, you want to make sure that the stress that's being applied, okay, is actually a stress. Okay. What I mean by that is there's a couple of different examples where they're saying we're applying the stress, but the stress doesn't actually knock you off of your K value. So we'll see some examples of that as we go forward. But essentially, this right here is the definition for Lechat's principle. Alright, so here's sort of a pictorial version of this. I got a reaction that's going back and forth between squares and circles. Therefore, my Kc value would be concentration of circles over concentration of squares. Calculate K would just be 1. Okay, so keep in mind, a stress for this thing would actually have to affect the concentration of circles and concentration of the squares. Anything that does not affect those two things isn't a stress. Alright, so now I got 2. Alright, so my Q here is going to be my products over reactants. So I got 1, 2, 3, 4, 5, 6, 7, 8. I got 8 over 2, which is 4. So now my Q is bigger than my K. So which way will it shift to regain equilibrium? It's going to shift that way. Okay, I have too much product. Alright, another way of looking at that is Q is bigger than K. They are a ratio of products over reactants. Therefore, my Q needs to get smaller. To get smaller, and you lose numerator, gain denominator, and therefore I will shift to the left. Which way will it look when you're done? Okay, well, to get back to 1, I would need to have equal amounts. I got 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, and let's see here, 8. So what is it going to be? 1, 2, 3, 4, 5, 6, 7, 8. Balanced? Okay. Do the picture here. So what happened in this thing on here? Well, I ended up losing. This is a really important drawing here. I lost my circles. and I gained my squares, and then I regained back my balance. Notice, a really important piece here, I'm never going to fall below my original value. Alright? Because when I added this stuff, okay, I have more stuff there. I can't go below that original amount. Hopefully that makes sense. Alright, so Lechat's latest principle continues. Now again, at this point, we're just going to start looking at stresses. How do we know if a stress is actually a stress? Okay, let's look at some examples. Adding and removing concentrations is the most common stress. Okay, and quite often they want to know, are you going to shift to left, right? Are you going to shift left, or is there going to be no shift? No shift, again, all that means is shifting to the right means I am going to be products over reactants, I'm shifting that. That means to the right. To the left means I'm shifting like that in order to regain back to equilibrium. So all we're going to really do is, whenever a stress is applied, we shift to undo the stress. Okay. All right, so indicate how Q is affected. Addition of B. Okay, so if I add B, B is a reactant, so it's products over reactants. I increased this guy went up, so Q is now, if it was that equal to before, now Q is now smaller than it was, smaller than K. If I remove C, alright, products over reactants, this guy went down, it's a product, so now once again, this guy gets smaller. Removal of A, alright, products over reactants, removal of this guy, now this thing gets bigger than K. How do I know it's relative to K? Because it started out the same. Right? How would these things shift in order to get back to the original? If I remove A, hold on a second here, I just noticed something. A is a solid. Nice, okay. So removal of A will have no effect on any of these things. Okay? Alright. My actual algorithm is K equals the concentration of C over the concentration of B. A is not included in this thing. So any change of A will have no effect, no shift. And be really careful. Actually, I should have missed that to begin with. Okay, so addition of B, we will see this will shift. Addition of B will shift to the right. That consumes B, produces C, and reverts Q back to K. Removal of C, shift the same way. All right. If gases are sensitive to changes in volume, calculate the current equilibrium constant. Okay, equilibrium constant here is they're both gases. K equals concentration of B, or partial pressure of B, over the partial pressure of A, and it's just going to be, and this is squared, so that's 1 over 1 equals 1. Perfect. Assuming those are equilibrium concentrations, which they are. Stress applied. The volume of the container is reduced in half, doubling the partial pressures. Okay, so now doubling the partial pressures goes to 2 and 2. Calculate the current Q caused by the stress. Okay, so now it's going to be 2 squared over 2. This is 4 over 2, which is 2. So now Q does not equal 1. Q does not equal K. So I am no longer at equilibrium, and I didn't even add anything. Okay, the volume of the container is reduced in half, doubling the partial pressures. Okay, it's stress number 2. Next one, the stress example number 1. The volume of the container is reduced in half, doubling the pressure. Okay, so different reaction. Okay, so I'm assuming this one goes to this one. This one goes to this one. Alright, guess we'll do that. I got that one done anyways. This is a little different situation here. Okay, so this one, my K value is equal to partial pressure of B over the partial pressure of A. There's no squaring here. The solid's not included. So I'm going to go from 1 over 1 equals still 1. Okay, double the volume. All right, so now, or should I cut the volume in half? I'm going to get 2 over 2 equals 1. In this situation, example number 2, I cut my volume in half and I didn't deviate from my K value. Same exact thing happened here, but I did deviate from my K value. Q still equals K. So the exponents on these things are super important. The coefficients are super important for this particular situation. All right, look at this guy. I got, okay, gas, gas, solid, same as the one right here. The volume of the container is reduced in half, doubling the pressures. Calculate the current of Q caused by the stress. All right. Because of the same, no change. I guess I have to make sure I know what I'm talking about on my own problem. No change. Calculate the current of Q. So Q is just going to equal K. They don't have any numbers here. This is why I know in general. The volume of the container is reduced in half. Because they're the same, it doesn't change. And this is the same as that guy. You didn't even change any numbers up. Alright, so pressures. So here we go. Let's try a couple examples of these. The volume of containers decreased in the following reaction. How will the concentration of C change as the reaction returns to equilibrium? Okay, so what I do in this problem is I look at only my gases. I got 3 gases over here, and I have 1 gas over here. And my stress on this guy is that, what am I doing here? The concentration of C, how will the concentration of C, the volume is decreased, so my pressures are increasing. So I want to reverse that. I want to reduce pressures. That's what I want to do. Shifting to the right goes to 1 particle 3. That increases pressure because I have more particles. Going to the right, left and right, 3 to 1, that reduces pressure because I have less gas particles. So I want to shift in direction to reduce it, and therefore this is the one that's going to happen. And this is if you calculate Q versus K, you'll end up at the same situation. All right, I'm undoing what I did. Right? I raised pressures, I want to reduce pressures. That's shifting to the right. The volume is increased in the following reaction. The volume's increased, so my pressures are going down. That's my stress. How will the concentration of C change as the reaction returns? Pause it, take a look. Alright, so notice here I have 2 gas particles here and 2 gas particles here. So they're the same. So this is going to have no effect on Q, no shift. No change in C. And this one, going to the right, C would actually go up. Make sure we include that to answer the question. No shift, C stays the same. Pressure on the system is increased by the addition of F. Okay. How will C be affected? Well, in this situation again, the Kp on this thing equals the partial pressure of C, partial pressure of, well, D is not included, and then partial pressure of A, partial pressure of B. So D is out, and F's not in there either. So I might be getting a total pressure more. So I have partial pressure total equals partial pressure of A plus partial pressure of B plus partial pressure of C, because they're all mixed together. And then I also add F, so partial pressure of F. Now what that does, the addition here increases that, that increases the total too, but does not affect the individuals that are present here, which of course are what's in the actual expression. Okay, the expression once again is Kp equals the partial pressure of C, partial pressure of A, partial pressure of B. Dalton's law of partial pressures, right there. Partial pressure total equals the partial pressure of A plus the partial pressure of B, yada, yada, yada. That's probably the hardest part of this whole thing. How does a catalyst affect a substance? Well, if your Q equals K, and you're already at equilibrium, what happens here? Okay, so basically reactants go into products, and we should note that what does a catalyst actually do? If you're here, okay, Q, it will reduce the amount of time it takes to get from Q to K. But Q, a catalyst, will not change K. Does not change K. Only thing that changes K is the temperature. Okay, temperature is that. So now we're not saying this. We're saying here is this: reactants, products. Remember, all these problems start where your Q is at the same spot as K. You're at the end. So if you're at the end already, how much would K affect getting you back to K? Well, you're already there. Sometimes I make a human analogy of a person being in a chair, and their person's just sitting there in the chair. And you say, okay, well, let me help you get back in your chair. I'm already in my chair. I don't need help. So how does it affect equilibrium? No change. Okay. How does temperature affect equilibrium? Okay. Now remember, temperature is the only thing that can affect the K value. So all of these things, it's not so much like I have reactants going to products, and then I have a situation where I have my K value, and my Q is there. I'm there. What the temperature does is it moves me to my K to a new spot. And now, it's kind of like the target changed. Now the old K is like, oh, well, I got to get back to my new spot. So I'm going to be possibly shifting one way or another because the target moved. All right, so A plus B is excellent reaction. So keep in mind, delta H is negative, and endothermic is positive. And I would just go ahead and add energy to the side that this marks what it is. And I would always treat these guys just like they're any other substance. Which way will the reaction shift if the substance is warmed? So what I do here is I take my thing, it's positive right now, so it's endothermic, and I say it's warm. So I'm adding energy. So I want to undo that stress. Adding energy means I want to remove energy. Remove all of this stuff. All of this stuff goes away, including the energy, and I produce more product. I'm going to shift this way. What happens to K? Well, K is a ratio of products over reactants, and I'm shifting that way. So K is going to go up. Okay, it's going to increase. The reaction above has a temperature decreased, and the concentration of C increased. So, what happened here? Well, first of all, if C increased, I shifted this way, and I added temperature. So if I add temperature, I'm going to be going away from the temperature. So the temperature must be on this side. And you can always just pick one. You could say, put it on the other side you want. So I'm adding temperature, I shifted this way. Does that make sense? Yes. If the energy was over here, if I add energy, I wouldn't shift, I would actually shift the other way and see it would go down. So this one's not correct. On this side, we are exothermic. Alright, these are some practice problems involving Lechat-Delay's principle, and our video is hitting 20 minutes, so we're going to stop there with our content. The rest of it is just practice problems. There are plenty of stuff in your workbook to try some problems, and we'll stop there for today. Thank you.